Hello, welcome back, everyone. Again, to this is track one, verification and validation. We had a very interesting first half of the track sessions on portable stimulus standards, two very great presentations. We are moving on to our third presentation of the day. The paper is a novel approach to achieve functional coverage, sanity, and efficient transaction level debugging for SoC design verification. Authors are Ratan, Harsh Setia, and Shreya Seth from Samsung Semiconductors India R&D. Over to you. We'll start with the paper three of track one.
Hello everyone, I am Ratan. I have Harsh and Shreya with me. We are part of SSIR, Samsung Semiconductor India Research. Today in this work, I am going to talk about a new approach or a new solution to two of the major SoC DV related challenges, which are functional coverage, sanity, and transaction level debugging. So before moving on to the main part, let me talk about the agenda. So moving on to the agenda, we will look at modern day verification, DV techniques being used and related challenges. And then we will have a look at the existing solutions, followed by the solution which we are proposing, some data from deployment and results, and next step for future. So at present day functional capabilities of a modern day SoC are increasing due to huge competition and demand present in various fields, sectors like AI, ML, consumer market, automobile. Chips are getting smaller day by day, but they are getting more stronger in terms of aspects like performance and power. The increasing capabilities uh, leads to a number of challenges before ASIC engineers. Time to market has always been a challenge, major point, but now with growing competition, it has become very important as development cycles keep shrinking. Not only that, many times product specification also change dynamically, which adds cherry to the cake. Designs are becoming more complex owing to small area and more functionalities. With all these challenges put before, there are uh, a, a set of expectations which are put before any verification engineers, where they have to execute a robust verification with stringent timelines without compromising on the quality of verification, leaving no bugs behind. And to do that, they are expected to optimize the process, use latest methodologies to save efforts and time, like accelerated test bench or emulators. To make verification efficient and robust, there are a number of techniques being used across our industry. We have formal tools, which is assertion-based approach, a DV approach, which with its own limitations. Then we have simulations, which are traditional approach. For functional verification, majorly simulation is being used across our industry. Coverage-driven verification is most widely used approach where input stimulus is limited and filtered using constants. In this approach, we try to excite only relevant part of the design feature and try to see if important scenarios are getting covered by looking at the coverage score. And in this approach, verification sign-off criteria includes two important factors. The first one is linear random regressions, where all test cases are run over a number of random seeds to target random points in solution space and then to achieve a desired coverage score to cover intended behavior of the design feature, which is the second factor. With random regressions, which initially result in many failures, failure analysis and debugging become major time taking effort. And if we talk about SoC level verification, transaction level debugging becomes very important as transactions pass through many stages like different bus components, bridges, cross paths, interconnects, and in if any transaction is getting corrupted at any given stage, it becomes really difficult to locate the exact stage to root cause the issue. Also, it becomes very time consuming and it involves manual waveform analysis, which is also dependent upon engineers' expertise, skill set, familiarity with the design spec. With respect to functional closure, we come across two aspects. One is coverage closure, another one is coverage sanitization, code fixes. So if we look at the IP level test benches, which are pretty small, coverage closure becomes a major time consuming task where we try to use some sort of automation to get directed cases generated by some sort of automation, some script to save human effort. But on the other hand, if I talk about the SoC level verification, it not only has coverage closure as major factor, but coverage code sanity also becomes a challenge at SoC level test cases. As SoC level simulations, they basically involve long compilation and simulation time from few hours to over a few days. And if I have to fix code and retry my fix, I'll have to wait for hours to get the results to see if my fix is really working or not. It may sometimes include a number of iterations. If I take smallest SoC test case for assumption, assuming it takes around 4 hours to run, I'll be able to do 2 to 3 iterations in a day to fix the code. This code can involve coverage monitors, coverage grid. This delay will definitely become a big risk to milestone and then to the project schedule. Now, looking at the existing approaches and their limitations to discuss challenges for transaction level debugging, a traditional approach is to use waveform analysis, which is a time taking approach. And additionally, we can use protocol monitors, but this can be one of the solution, but that would require extra effort for monitor integration, but also it will hit the simulation performance. Simulation time will increase. For coverage code fix or sanity, trial and error is widely used approach, because if there are issues in coverage, engineer will try to fix them and will try to read them. So automation can help in coverage coding, but full automation is not possible because coverage also includes coverage monitors where automation sometimes not possible. So with this, we have two major SOCDB challenges before us to solve, which are transaction level debugging and functional coverage sanity. And now looking at the solution, which we are proposing here, and we have tested it at our end, we have come up with a debugging tool which will generate an in-hand transaction status book containing information of all the transactions with specific timestamps from desired module interfaces. Having an transaction flowing summary in a readable format makes life easy. Instead of digging into the waveform signals, we can check directly at which stage transaction is breaking or getting stuck. For this, uh, the tool just requires two inputs which are already generated for manual debugging as well. We have waveform dump and the signal list. So it will produce an XLS containing transaction level information uh, at all the required interfaces which are mentioned in the signal list. Apart from having above feature implemented as the base feature, uh, tool also has other facilities. It has a facility to select a desired time window where the debug or the transaction level tracing can happen. And it has an option to select a number of interfaces from the signal list. Assuming we have 10 different interfaces signals, we need only 5 interfaces, so that can be selected. The tool has small runtime. Uh, it also has additional benefits of protocol checking. Assume we are trying to list out all 5 interfaces, and in existing test bench we don't have checkers for all the existing interfaces, and we might be interested in enabling the checkers for those interfaces, so that can also be done using this tool. And for FC sanitization, the good part is that this setup extends debug tool infra. It has small run times, so TAT is quite small. So if you have a smaller TAT, you will have time for more iterations. You can go ahead for more iterations if you're fixing the code, and also it will be reusing the existing simulation environment. And with this facility, it gives you a provision to fix and enhance the coverage grid as well as coverage monitor. Moving further, let us have a look at the implementation of the tool. So basically, this part of the diagram shows the normal flow as we do simulation in test benches. We get the FSDB files, and so we have a signal list here, and so this is the normal flow. So the intention of the idea was to get the required transaction list using only these inputs. So we thought of a mechanism where we can replay the waveform. So as we know that waveform is having information about all the signals and their transitions based on time. So we needed some mechanism to replay the waveform on coverage monitors and to get the transaction information from the monitors. So for that, first we implemented our own utility by converting uh, encoded waveform databases into VCD format, which is directly readable format. And with that, we had another challenge that was to dump an automated test bench, which will have all the VIP instances with all the required configurations. So we wrote automation for that. So that automation extracts information from the file list and from the waveform database. It tries to create a test bench on the go. It will try to instantiate all the required monitors, all the required configurations into the VIP. And then this replay utility does replay the entire waveform on the system. And we will get the logs from monitor files. And once the data is ready from the monitors, it can be extracted using automation. So finally, we'll get the transaction list here. And so, so So it will be easy for any engineer to process the final list of transactions. He can have a look for the specific transaction which is failing or which is getting stuck. A similar mechanism is used here also in coverage sanity setup, where waveform database is played over coverage grid and coverage monitor. So instead of replaying it on auto-generated test bench, so here we are trying to replay the waveform on existing coverage model and coverage monitors to see if fixes are working or not. So instead of running the whole simulation on existing test bench, bigger test bench, we are running the waveform on a very small test bench where only required interfaces are there and only required VIP instances are there. So by this way, our TAT will come down to a few minutes from few hours. Moving on to the case study or the experiments which we conducted with the tools. For debug tool, we picked a subsystem level dump, which was of 8 GB and overall simulation time was around 1 millisecond. It had multiple stages, and so we selected 5 AXI stages where trace was run over a period of 20 microseconds. For FC stabilization, a medium level SoC environment was picked, where it had multiple stages, but the coverage was written only on 4 AXI and 1 APB interface. So, and also third-party utility, replay utility was used. We had our own utility as well, but meanwhile we got it from vendor as well, which would be more efficient since we are using their simulator. So we started using their utility, and total number of bins were around 1K, where 20 cover groups were there. So here, as on average, we are assuming that we need 10 iterations to fix these many cover groups. That fixes include fixes for cover groups and coverage monitors. Now let us check the results. So debug tool overall took 3 minutes to run, and this time was taken with 10 different iterations. So this is the average time taken by the tool over 10 iterations over 10 different instances, and tool was able to extract around 1000 plus AXI transactions. So with the given list, you can see here, this is the list given by the tool. It becomes very easy to get the faulty transaction. So this list will contain the complete transaction details. So here in case of AXI transaction, we can have a look right for each stage the transaction is mentioned. So here you can see four different stages are mentioned. So for each transaction, the address phase, data phase, and the response phase, when it happened, what is the data ID, and what is the completion time. So every point of detail can be found out from each row, where each row is representing each transaction and on relevant stages. So with this information, it becomes very easy to figure out the faulty stage or the faulty transaction. And if we talk about the improvement factor, which is calculated basically on a number of average debug efforts. So 3 to 5x improvement factor is observed when we compare it to the manual debug. So in case of manual debug, uh, the effort will be around 40 to 45 minutes when there are 5 AXI uh, stages and manual debug is going on, and we have to find out the stage. With the tool, it will take only 10 to 15 minutes because tool will take around 3 minutes to run, and rest of the time can be taken as debug. And since it's in the readable format, it will take very less time for debug. If we compare these results with the monitor-based approach, where monitors are instantiated in the test bench, VIP monitors, to extract the transactions. As we already discussed, it will take extra time to integrate the monitors and then finally get the results. And also with the monitor logs, we have to extract further information. We have to analyze them manually. So it will take more time. So with compared to monitor technique, this improvement factor will increase, it will be more than 5x because of monitors hitting the simulation times as well. Looking at the FC stabilization results, we could see a overall improvement factor of 9.43x in terms of turnaround time. So here total test case run time was around 242 minutes, which was most optimized with save and restore technique. So if we look into the below graph, on x-axis we can see average number of reruns to fix the code, and on y-axis we can see number of minutes, or we can say overall rerun time for each iteration. So if we observe this graph, we can see that with a number of iterations, number of overall rerun time is increasing. So if any engineer is requiring only one rerun, then it will be similar in case of manual or tool-based debug. But if the engineer is going for more number of iterations to fix the coverage code or coverage monitor, definitely this time will keep increasing, and you will find this graph. In case of tool, since we are only simulating a part of the test bench, which is having only relevant VIPs, and we are driving only the interfaces on coverage grid and coverage monitors. So the runtime will be very, very small. It will be, in this case, it was around 3 minutes. So here you can see for each iteration with tool, we can add 3 minutes. So it will be almost linear in this way. It will be almost horizontal. Whereas if we don't have the tool, we go for the full simulations, the time will keep on increasing with each and every iteration. And if I assume there are 10 iterations to fix 1000 bins, then the improvement factor will be around 9.45, 9.43x. Moving on to the last section of the presentation. So here we will look at the future scope or next step for the future. So GUI-based platform can be explored for this tool, for the debug tool, for easy transaction identification. And then once the data is ready, more data mining algorithms can be run on the tool to extract more informative conclusions, like performance estimations, and also validity analysis can be done based on transaction attributes. As of now, this tool is implemented only on AXI protocol, but moving further, we can implement it on other standard protocols like ABB, HBAS, and other new protocols like CHI. Uh, Tool performance can further be improved with save and restore utility, where snapshot is saved up to a point, which is common across all the test cases, and from there the test case reruns. But this with this technique, as of now, tool has not been run, and it is still to be explored. So that's all from my side. If you have any questions, please do let me know. Thank you, everyone.
Hello, great presentation, Ratandip and team. Let me just quickly get started in the interest of time on a couple of questions that are coming our way. So one of them is there a way to look at the transactions without generating waveforms? Waveform generation could be time consuming. And any thoughts on that?
Hello.
Yeah.
Sandeep, could you please repeat your question?
Yeah, so there's a question which says waveform generation or waveform dumping,
Mhm.
is it a must, or can there be a way to look at the transactions without the waveforms, generating the waveforms? It could be time consuming.
I think waveform generation will be the bare minimum required thing. So here the thing is we need transaction level information. So we are trying to debug. So this approach is related to kind of manual debug. So in case of manual debug, if we have a transaction getting corrupted at any particular stage, so we will have to generate the waveform, right? That will be the bare minimum thing if you don't have the coverage monitors,
Coverage
right?
mode.
And in SoC level, there will be multiple stages. So even though you have coverage monitors in place and you'd like to go ahead with the log files, so at the time of debug, you won't be knowing where exactly what interface the coverage monitor should be enabled in the single test case. So definitely coverage for this thing waveform dumps will be needed.
Okay, sure. So one another thing, Ratan, I mean, something that I was curious to try. Will this scale with the complexity of the design or the test bench? I mean, how complex was your designs? I know you didn't mention about 5 stages of AX and all that, but will it vary with respect to the change in the design sizes itself or the test bench complexity, system scenarios, and things like that? Any take on that?
So Sandeep, I'll try to answer that. Harsh here. So firstly, like as for the previous question, Ratan was mentioning coverage monitors. So it's not coverage monitors, it's actually a passive UVC monitors. That's what he was referring to.
I see.
And in this particular for this particular question, if I may try to answer, if you consider the bigger the size of the SoC, the bigger the runtime is.
Absolutely.
And when you try to capture a lot of interfaces, see for us, it's kind of an application processor kind of a design where our runtimes vary somewhere close to 4 hours, and with power test cases, it can go up till days. So that's the scale which we are trying to conquer. And in this particular context, the thing is, anytime I have to run, if I instantiate a lot of VIP monitors to go the log way, it is kind of time consuming, because for every interface, if I do that, there are probably these monitors will run in thousands, and there will be a lot
Thousands.
of callbacks that would be there. So it will slow down the simulation tremendously. And then without having a look at a waveform, it's very difficult for a verification engineer to trust the VIP completely. In certain cases, we do that, but
Right.
then as a practice, as a verification engineer, we do look into the waveforms.
That's
So
right.
believe it or not, waveform has to be there. And if it is there, what we are trying to do is we are trying to leverage on that and avoid reruns, whereby also maintaining the simulation speeds are acceptable. We don't slow it down. So that's what we are trying to do. And as the scale increases and as the number of interfaces increases, we need more runtimes. We need more VIP monitors. And with both these, the simulation times will further increase. So that's where we are trying to bring this in, where we'll have the waveforms ready, whatever are the interfaces of interest. We will go ahead and we will just tap those and give it to our tool and tell them, was you generate the transactions over here and ensure the protocol sanity is maintained.
Okay.
So that's something which we are trying to do here.
Absolutely, Harsh, and thank you, Harsh, for taking that question. And this is a very key initiative or technology, because debug is a significant part of the verification turnaround time reduction. So this is pretty much falling there.
Right.
Thank you, and definitely there were a few questions related to how we could use the save restore, but I did see that in your future work. So in the interest of time, I will have to cut this short. Again, a very great presentation, Ratan, Setia, and Shreya Seth from Samsung Semiconductor India R&D. Thank you.
Thank you.
Thank you, Sandeep. Thank you, everyone.